Hello everyone. In the last lecture, we have seen some examples based on the singular integral equations. Okay, the PDF was shared. So, in this video, we will start with a new topic, that is integral transforms. And for this integral transforms, I need something called as Fourier transforms. Okay, and for those Fourier transforms, how do we derive the Fourier transform and what is a Fourier transform? These videos were already shared with you all. Okay, so now let us begin with this new topic, integral transforms. What we will be doing is we will use the Fourier transform and the Laplace transform formulas in order to find out the solution of integral equations. Okay, and if you remember, we had seen something called as convolution kernel at the start of the course. Okay, so if we have the integral equations which have the convolution type kernel, okay, specifically the convolution type kernel, then there is a very easy method to solve those types of equations by using Laplace transform. Okay, so we will study that, and as you can see, we will be dealing with all these transforms and hence the name integral transforms. Okay, so the integral transforms methods are of great value in the treatment of the integral equations. Okay, especially in some cases we will be coming across the singular integral equations. Okay, now suppose we have a relationship which is like this: y of x equal to double integral this gamma of x comma s k of s comma t y of t dt ds. Okay, now suppose that if this relationship is true, okay, that is, this relationship, if we consider it to be as a valid one, and that this double integral can be evaluated as an iterated integral. Okay, so now you can see this equation. Look at this equation here: f of x equal to integral from k x comma t y of t dt, and the equation y of x to be equal to integral gamma of x comma t f of t dt. Okay, now suppose if I take this as the integral equation of first kind, okay, then if suppose I want to find out a solution of this particular equation, okay, I already know that this relationship is a valid one. Okay, that means double integral of gamma x comma s k s comma t y of t dt ds, this gives us y of x. Okay, suppose this is a valid relationship. Now I am thinking about finding the solution of this integral equation. That means I want to find out one such f of t such that if you put that f of t here, we will get the answer as y of x. Okay, see, I am looking at the integral equation of first kind. Okay, and you can clearly see here I can treat this as the integral equation of first kind. Then this will be that non-homogeneous part, okay, because on the LHS in first kind it is the 0, right? So if this is the integral equation of first kind and I want to find out a solution of this, so what I want to find out? I want to find out one such f of t such that if I put that f of t here, I should get the answer of this particular thing as y of x. Okay, now if you observe carefully and see, if we take this as f of t, okay, f of x is this, so what will be f of t? F of t will be integral k t comma x. In place of x I am putting t, so this t, then there is a clash of notation, so let me take this to s, so s y of s ds. Okay, so if I take this as f of t and substitute it here, what we will get? We will get double integral gamma of x comma t, then this, right, k of t comma s y of s ds dt. Okay, after doing the proper interchange of the integrals, okay, then we will get this expression. And now you can see this expression, compare this one and this one. Okay, so in order to simplify this comparison, let us change t to s. Okay, so wherever there is t, let me put it s here. Okay, so wherever there is t, we'll put s, and s we will put it as t, so ds and dt will remain. So now if you see this expression and this expression, both are the same. What is it? Gamma of x comma s, gamma of x comma s, k of s comma t, k of s comma t, y of t dt ds, dt ds. Okay, because this will be changing to t, this will be changing to s. Okay, so if I take this f of t as this expression, then I get a solution of this equation. Okay, so in a similar way, we can also check that if I consider this as the integral equation and if I take y of t to be equal to this, then this comes out to be the solution of this particular equation. Okay, so it's like this will be a solution of this, this will be a solution of this, provided such a relationship is known as a valid one. Okay, so that is how we will be dealing with the integral transforms. So one can be called as the transform and the other can be called as the inverse transform. Okay, so to understand that, now I will write the Fourier transform expressions, which you all have already seen in the previous videos. Okay, so then you will understand it better. So you all must have already seen this expression in the previous video. F of x to be equal to 1 upon 2 pi integral from minus infinity to infinity, then integral from minus infinity to infinity f of t e raised to I alpha t dt e raised to minus I alpha x dt alpha. Okay, such an expression was there in it is equal to f of x. Okay, and then what we did, we called this part as f of alpha, so that was f of alpha, which is integral from minus infinity to infinity f of t e raised to I alpha t dt, and this 1 upon 2 pi we will write it as 1 upon root of 2 pi into 1 upon root of 2 pi. So 1 upon root of 2 pi I will take it along with this. Okay, so now we get this expression. So this was called as the Fourier transform of the function f of x, this f of x. Okay, f of x, Fourier transform of the function f of x. And what is the formula of that? It is this. Whatever is that f of x, you put it here by replacing x by t into e raised to I alpha t dt. Integrate it with this constant. Whatever answer you get, that thing is called, will be a function of alpha, and it is called as the Fourier transform of the function f of x. Okay, and once you get this, you substitute this here. Then what you get? Then you can reobtain the function f of x. Okay, so therefore this is called as the Fourier transform, and the other formula is called as the inverse Fourier transform. Okay, so in that we get what is f of x. So how do we get that? 1 upon root of 2 pi integral from minus infinity to infinity f of alpha, means what? This full expression f of alpha, okay, into e raised to minus I alpha x d alpha. Okay, so this is called as the Fourier transform, and this is called as the inverse Fourier transform. Now let us look at how we apply it for the integral equations, okay, and solve the problems, because we are mainly interested in finding the solution of only the integral equation by using these two formulas. So, solution of integral equations using Fourier transforms. Now, before going actually for the problem, what I will do is, I will just quickly revise what is Fourier sine transform and Fourier cosine transform. Okay, now just now we saw the Fourier transform of the function f of x. Similarly, there is something called as Fourier sine transform of the function f of x and Fourier cosine transform of the function f of x. Okay, so the infinite Fourier sine transform of capital Y of x, instead of f of x, no, here it is y of x, where the x is ranging from 0 to infinity. Okay, so this sine transform is defined as integral from 0 to infinity whatever the function is into sine px dx. Integration is with respect to x. Okay, and this is px. So you can clearly see that this will be a function of p. Okay, and it is nothing but Fourier sine transform of the function y of x. So the symbol is this, Fourier sine transform of the function y of x. So y s of p. Okay, or in other notation it is written like this, Fourier sine transform of the function y of x. Then what will be the next thing? The next will be, if we want to find out what is this function y of x. Okay, so what will be the inverse Fourier transform, and the corresponding inversion formula is this, y of x is 2 by pi integral from 0 to infinity whatever is that Fourier sine transform into sine px dp. Okay, so suppose if the Fourier transform of some function is directly given to you and you want to find out what is that function, then you will have to use this formula. Okay, so the notation is inverse Fourier transform of this thing is given by 2 by pi integral from 0 to infinity ysp. That means the Fourier sine transform of the function y of x is this, into sine px dp. Okay, so this is nothing but y of x. This will give us the y of x. Now the same thing is followed for the cos function. only in place of sin px we will get cos px, no any other difference. Okay, so similarly these two formulas. Now let us go for the problem. Solve integral from 0 to infinity capital F of t sin st dt equal to this. Okay, so you can clearly see here we are given that this expression is equal to this. That means this must be the Fourier transform of the function f of x, capital F of x. Okay, so you can clearly see that this particular thing is the Fourier transform of this particular function. Okay, and we want to find out a solution of this particular equation. Okay, so if I want to find out a solution of this particular equation, you can see that it is an integral equation. Why it is an integral equation? Because this is the unknown function which is appearing inside the integral sign. And further to that, you can also see that this is a integral equation of first kind. How is it? See here, this is a known function, this is sin st, and this is unknown function. Okay, this is working as a kernel, right? Because it's the function of two variables s and t. Okay, and this can be treated as the non-homogeneous part. Okay, because what is the standard form of first kind integral equation? We write it like this, no? F of x equal to integral k x comma t y of t dt, and our aim is to find out what is this y of t, that is a solution. Okay, so in this case this xt is st, and here yt is there is this capital F of t, and this f of x is nothing but f of s, variable s. Okay, so it is that, and hence this is an integral equation and we want to find out this. Okay, so we have a nice formula for that, because this is nothing but the Fourier transform of this particular function, and now I want to find out what is that function. So what we will do? We will use the inversion formula, that is the inverse Fourier transform formula, which is this. Okay, so Fourier sine transform of ft is given, that is this, which is what here. Okay, so this is exactly equal to this, no? Because it's the Fourier transform of this particular function. So how do we find out what the function is? So this will be inverse Fourier sine transform of that thing, the function, this. Okay, so it is that particular thing, which is nothing but 2 by pi integral from 0 to infinity, that function whatever it is, that means this, into sine of px. So here sine of st we will take, because the variables are different, no, here. So sine st integration with respect to s. Okay, whatever is this variable, integration is with respect to that variable, keep that in mind. Okay, otherwise you all might integrate this with respect to t, and then this s will start acting as a constant and you will go wrong. Okay, so whatever this function is of whichever variable, that variable you have to take it for integration. Okay, similarly see here, whichever variable is there for this function, that will come as a integration variable. Okay, so what is this? It is nothing but this, no? So on different intervals it is defined differently, and our interval is from 0 to infinity, but you can see here on s greater than or equal to 2 it vanishes. So we will be getting integral from 0 to 1, then 1 to 2, and remaining is, after that it is 0. Okay, so on 0 to 1 it is defined, it was 1, so it is 1 into this will remain, plus 2 into this, then it's the simple integration. You can go through this and we will get this answer. So this will be our f of t, which is a solution of this particular integral equation of first kind. Okay, so one more solved problem I will share with you all, and I'll also give you the exercise problems.